AI Finance Portal number 3, Acropolis. The Greeks of Black-Scholes. The world owes much to the Greeks, particularly those of the city of Athens, the cradle of democracy. The citizens of Athens congregated on a hill in the center of the town called the Acropolis, the high city. We get the words politics and police from the second half of the word. Greece is also the source of our modern theater, and each of the Black-Scholes Greeks will be playing a role today. I renamed the master Black-Scholes code template Acropolis because the code is a map of the high city where we shall meet the Greeks, so critical to all derivatives transactions. We need to get the risk-free rate if we're going to do the calculations and look at the prices. The risk-free rate today is 4.27%. We use Yahoo Finance here to fetch our options data. We have the ticker down here. We're going to use NVIDIA today. We need the stock price, the strike price, the time to maturity. So we're going to go back up here a little bit, and it gets the first option in the options chain. Okay, so it's the earliest expiration date. So down here, the data that we've pulled for NVIDIA. Here's today's date. The stock price is 107. I peeked at it a couple of seconds ago. It's dropped down to 106.46. Here's the time to maturity for the option. The option expires in 3 days on the 4th. So we're actually do the calculations here. There's the risk-free rate that we got from upstairs from the Federal Reserve. And this is the volatility. We bring all this options data down from Yahoo Finance. And from a programming perspective, it's nice to know which global variables are available. Here again is the Black-Scholes model. We're going to calculate it using NumPy and SciPy stats. Here is where some Nobel Prizes have been awarded and the fertile ground for those pursuing their PhDs. Now, from the data that we've brought down, we can calculate these Greek values. And for delta, we can think of our Greek character as the guide. The delta measures the sensitivity of an option's price to changes in the underlying asset. A delta of 0.5 means the option's price moves 50 cents for every dollar in the change of stock. So it's moving quite a bit more than that. The gamma here, we can think of this as the sculptor. This tracks how the delta changes as the underlying price moves. If delta is the speed, gamma is the acceleration. Gamma is pretty high here also. Vega, we could consider this the oracle. It measures how much an option price moves with the change in implied volatility. Higher vega means greater sensitivity to volatility shifts. The implied volatility comes down with the data. And then theta, which we didn't calculate here, is important. This is our rho. Theta is a timekeeper, and rho is like the treasurer. It measures an option's price sensitivity to interest rate changes. So I had to go back because we weren't getting the calculation for the theta. Theta represents the time decay, the rate at which an option loses value as expiration approaches. So the theta is pretty high here because it's going to expire in 2 or 3 days. So we're going to learn how options work. The rho here measures an option's price sensitivity to interest rate changes. So we're going to figure out what these numbers mean in sort of a reverse order of understanding how Black-Scholes works, because we're getting the AI to generate the code for us, and we have to figure out what these numbers are telling us. And so at this point, it's really nice to have an options expert step in here so that he can design the application, or she can design the application that's going to send them a greater number of options for them to consider, and train the ML to pre-screen the options for them. And that way they'll be able to multiply their throughput by 10, 20, even 50 times. Again, this code generation ability is awesome. We're going to do a lot more with the Greeks. Today is just a brief introduction, and we'll go through these one by one to figure out how they fit into our investment schema. Thanks for your time.